Hello everyone and welcome to my lesson on forces. We're going to start the lesson like normal with a quick quiz. If you want to pause the video and have a go, the answers will be on the next slide. Check your work and correct any mistakes that you've made. Okay, today we are going to be looking at forces. The very first thing about drawing them, the idea of a resultant force, and then we'll be looking at naming forces. Have a think about what is meant by a force. You've used the word before, you've heard it before. What is it if you had to put it into words? What would you say? And then have a quick recap about what a scalar and a vector is. If you want to pause the video, you can. A force is a push or a pull that acts on an object due to the interaction with another. So you need two objects here. You need something to push it or to pull it. You need two objects to make a force. We would say that one of the objects exerts a force on the other object. Scalar is a quantity that has magnitude only. Magnitude means size. And that's that with a unit. So for example, mass is a really typical scalar. It's 5 kilograms. You can't have 5 kilograms to the left. It doesn't have a direction. It just has a number and a unit, 5 kilograms. A vector is a quantity that has magnitude and direction. So magnitude means size and direction is direction. So you will need to include an arrow or to the left or up or north or something. But if it has a size and direction, that's a vector. And if it has size only, that would be a scalar. The first thing we're going to look at is the idea of a resultant force. A resultant force is a single force that you can draw that's exactly the same as all of the other forces added together on the object. For example, if I had an object that looked a bit like this, a circle, and I drew one force on here like this and another force on here like this. So imagine these were both 5 newtons and 5 newtons. Then you can add them together and it's exactly the same as drawing one single object, oh that's meant to be the same, with a force of 10 newtons. And this is because forces are vectors. So you can add them together if they're in the same direction. So 5 to the right and 5 to the right would add together to make 10 to the right. If you want to, and you're thinking in the opposite direction, so for example I had another object here, and I pulled to the right with 8 newtons, and to the left with 2 newtons, then those two, because they're in the opposite direction, you can subtract them. So 8 to the right and 2 to the left is exactly the same as drawing an object with just 6 to the right. This one here, this is called the resultant force. That 6 is exactly the same as the 8 and the 2. So we're trying to work out what's left after you add everything and take everything away. What one force is left at the end. Let's do another example. If I had another object, and I'm going to draw, let's say, 20 newtons to the left, to the right, and I'm going to do 10 newtons to the right, and then I'm going to do 16 newtons to the left. What would the resultant force here be? Well, the 20 and the 10 can be added together because they're in the same direction. That will make 30. And then the 16 to the left would be subtracted because that's going in the opposite direction. So that's exactly the same as if I did the object with 14 to the right. 14 newtons to the right. That's the resultant force. If you add all the forces together on an object, that's what's left. Now, something that's quite important on my slide that doesn't look as important as it should be is the length of these arrows. So, for example, if you have a look at my picture at the top here, the red one, this 5 and 5, they're the same length. That's important. And the 10 should be twice the length. Because it's twice the size, it should be twice the length. Mine's not quite, but nearly. Now, if you have a look at so this one here should be the same as this one here. And it should be exactly half this one here. If you have a look at my blue shape on the top right, the 8 here should be about 4 times larger, or should be exactly 4 times larger than the 2. And the 6 should be a bit less than the 8. Really, the 6 and the 2 should add up. So the length of this line really is important. We need to make sure that it's important on every diagram you draw from now on. Now the 20 and the 10 in the bottom left, that's about half the length, so that's okay. The 16 should be longer than the 10 and shorter than the 20. I'd say the 14, that's a bit too long. That's nearly 20. So that one's wrong. Okay, we're going to do one more example in purple, and this is going to be a last object. It doesn't actually matter which direction we go, as long as we go in the same direction. So it's like we can go forward and back or up and down, but we don't want to mix those two yet. So this one is going to be, let's say, 4 newtons that way and 3 newtons that way. And I'm going to pull down with a force of 1 newton that way. Now that's exactly the same as drawing another object, the same object, and that will be 4 plus 3 is 7. And minus 1 would be 6 newtons forwards. Now when you draw it, be careful of your arrows. My 6 is less than my 4. That's wrong. It should be longer. But just be careful whenever you're drawing your diagrams. Okay, I've got 4 more examples here. I'm going to practice 4, and then you're going to practice the next slide. So the first one I'm going to do up here is I'm going to draw the resultant force of these two. Here's my box. It goes 10 to the right, 8 to the left, so the resultant is 2 newtons to the right. So there's 2 things you need here, number and direction. And that's because forces are vectors. The resultant force of this one, got our box, it's exactly the same. 5 up, 3 down is the same as 2 newtons upwards. Okay, this one down here. We've got our box. We've got 6 and 9 upwards, that makes 15. And 5 going down, so the resultant force will be 10 newtons upwards. And the very last one, we've got 20 to the right and 50 to the right, that makes 70. 70 to the right and 6 to the left. So 70 to the right minus 6 to the left. So we'll have 70 minus 6, which is 64 newtons to the right. And I'm trying to make it a bit longer. It should be longer than that. It's not much longer than the 50. And in fact, the 50 and the 20 are the same length. That shouldn't be right. The 20 should clearly be less than that. But when you draw your diagrams, make sure you get a length of the arrow that represents the size of the number. Okay, that's my 4 examples. You are going to practice on the next slide. If you want to pause the video, feel free. Okay, if you've had a chance to have a go at these, I'll go through the answers now. The one on the top left, we've got 10 to the right and 6 to the left. So the resultant force is exactly the same as 4 newtons to the right. Now, do you see here we've got a size and a direction, 4 to the right, and that's because forces are vectors. 10 minus 6 is 4 to the right. Now you can clearly see that these two boxes are equivalent now. We've got 10 and 6 is exactly the same as if there was one box with one force of 4. Okay, 15 to the left and 2 to the right is exactly the same as 13 newtons to the left. Next one, 80 up and 70 down is exactly the same as another box with 10 newtons up. So we need a size and a direction because force is a vector. Okay, this one, we've got another box as the resultant. We've got 60 plus 50 is 110. 110 plus 20 is 130. So I've got 130 pulling to the right. And I've got 100 pulling to the left. So 130 right minus 100 would be 30 newtons to the right. Next one down, 15 up plus 3 up is 18 up. Draw my box first. We've got 18 up and 5 down is the equivalent of 13 newtons up, and that is the resultant force. Last box. We got 9 to the right, 11 to the right, that makes 20 to the right, and 20 to the left. Oh, interesting. 20 to the right and 20 to the left. That means this box has no resultant force. No resultant. No resultant. Oh, no resultant force. Now that's a good thing. Happens a lot in physics. We call this a special name. It's called equilibrium. And that's when all of the forces are balanced. So that doesn't mean there's no forces acting on the box. There are forces, but they're balanced. We've got 20 to the right and we've got 20 to the left. Okay, looking at equilibrium one more time. If we have a box with all of the forces balanced, on the left it's 10 and 10, they're balanced. And on the right we've got 4 to the left, 4 to the right, that's balanced. If they were on the same side, that wouldn't be balanced, we'd add them. But because we can subtract them and they're in opposite directions, the one on the left is called, the object is in equilibrium. And the one on the right is in equilibrium as well. All the forces are balanced on the left and all the forces are balanced on the right. And the word's right at the top here. Equilibrium. Equilibrium. Bit like equal, I guess. Equal. Equilibrium. Okay, moving on to the next part. We've done about resultant forces, now we're looking about naming forces. Naming forces is super important. You need to know the names and how to draw each force. The first thing you're going to pick out is weight. It's used all the time. You need to know exactly how to draw it on an object and its name. Now some people call it gravity. Gravity is wrong. It's not gravity. Gravity is not a force. Gravity is the thing that pulls you down. The Earth has gravity and it pulls you down, and that causes the weight. So don't name it gravity, that's wrong. We're going to call it weight. You could call it the gravitational force or the force caused by gravity. But weight's just a better word. It's a technical word. So we're going to use that. Now if you want to draw it, we've got two objects here. We've got a ball and we've got a person. You want to draw it from about the middle. So the ball, you can see that the arrow starts in the middle and goes directly down. Every arrow must go directly down. And the person, I'm starting from about their waist. We'll look at exactly where to start it in a later video. But for now, we're going to draw it in about the middle. So middle of the object goes straight downwards. And that is called weight. So we'd label that W. The second force we're going to name is this one. Now it looks exactly the same. Now the ball is pushing down on the floor. Now if there was a force there just pushing downwards, it would start going downwards. It would start accelerating downwards. Now it's not doing that. The ball's just stopped. The person's just standing still. So therefore there must be a force pushing backwards. If the weight is pulling it down, then there must be a force pushing it up to make it balanced. We would say that the ball and the person are in equilibrium. So therefore there must be balanced forces. And if there's a force down, there must be a force up. And this force that pushes up is called the contact reaction force. And we draw it like this. So the arrow starts from where the contact is. So where the ball touches the floor, that's where I'm going to start my reaction force. And with the 2 feet, the force would get divided into 2. So the force pushes up from the floor onto his feet. And because he's got 2 feet, there are 2 arrows. But remember about the length. The length of this arrow here is the weight of the man. And the weight of these two, the size of these 2 arrows here, these 2, this one here, number 1, and this one here, number 2, those 2 should add up to the weight, the size of the weight. So for example, if that was 100 newtons, then this one would be 50 and 50 newtons and 50 newtons. They would add up. Because he's in equilibrium, we know that the 2 reaction forces, or the 2 contact reaction forces, are equal to the weight. So the person is in equilibrium, and the forces are going to be balanced. Have a practice on this one. We've got a car. The 2 forces we learnt so far are going to be these. We've got the weight going from the middle downwards, and we've got the contact reaction force going from the contact. So where the tyres touch the ground, that's where we start the force from. And remember, the length of the weight arrow should be equal to those 2 arrows going up. Now this is for a car that wasn't moving. But if it was moving, if it was driving down the motorway at 70 miles an hour, there would be more forces. So we're going to do those now. These are the next forces we're going to learn about. The first one we're going to look at is friction. Friction down the bottom here. Now friction acts between 2 objects whenever they rub. So if there was the tyre on the ground, that is the cause of our friction force. Friction generally acts in the opposite direction to which you're travelling. So if the car's travelling, the friction will be backwards. You might feel that friction force. If you rub your hands together really, really hard, you can feel that force there. That force might start creating some energy there, some thermal energy, and your hands will start to get hot. But the friction is whenever you get two surfaces in contact with each other. The one at the back is called our air resistance or drag. Both of these words are okay. They're technical words. Some people think drag doesn't sound very technical, but it is. Air resistance and drag are technical words, and you can use either. They're both good words. Now, air resistance is the air pushing against the car. The faster you go, the more the air pushes you, so the drag will start to increase. Now, the one from the engine at the front doesn't really have a name, so we're going to call it the driving force for now. And don't forget the other arrows, the weight and the contact reaction force, are still there. Okay, 2 more forces. On the left, we've got tension. Tension is the name of the force whenever you're pulling an object. So normally it's a rope. It could be a chain or a spring. It could even be an iron bar. If you're pulling anything, that's tension. It could be a tow bar. If you're pulling a caravan, your tow bar is going to feel a force, and that will be a tensile force. We'll call that tension. That's different from compression. That would be squashing. This is pulling. So whenever you pull an object, there'll be a tension force, and that will exist here. Second one we're going to talk about is upthrust. Upthrust is the force that pushes up on an object that floats. So it's sort of similar, to the contact reaction force. When we had the car earlier, the floor pushed up on the car. Now on here, we've got the weight of the boat pulling downwards. The weight of the boat pulling downwards, and then the water pushes back on the boat, and that we call upthrust. Now again, look at where the forces are starting. The weight starts in the middle of the boat going down, directly down to the center of the earth. And upthrust is where the contact is with the water. And they're equal because the boat's not sinking, it's not shooting up into the sky, it's in equilibrium. The forces are balanced, so the length of those arrows are exactly the same. Okay, pause the video, have a go, draw your object, then add all of the forces and their names, and then check my answers with yours and correct them if you need to. Okay, we're going to go through some of these answers. So the skydiver on the left. The first thing I'm going to draw is, I'm assuming it's falling down. I'm going to assume that he's falling down to earth. He's just jumped out of the aeroplane. So the weight is going to go from his middle directly down to the center of the earth, and that would be my weight. Now he's only just stepped out of the plane, so there will be a little bit, I'm going to draw it from the back of him there, there's a little bit of drag. I'm going to draw that drag, D for drag. And he's accelerating down to the center of the earth. That's where the arrow is going for his weight. So we've got weight going down, drag going up. And he's falling down, so drag always goes in the opposite direction to which he's traveling. Next one, we're going to do the apple. The apple's just sitting on the table, so I'm drawing weight from the center, going directly down towards the center of the earth, and we'll label that weight. And the table is pushing back on the apple. It's stopping the apple falling down. And because the apple pushes the table pushes back on the apple, and it pushes upwards. And we're going to write R for contact reaction force. It shouldn't be a squiggly line, that should be a straight line. But they should be equal lengths. So the weight going down and the contact reaction force going up are balanced. This object is in equilibrium. Okay, let's do the next one. We're going to do the motorbike. Motorbike starts off with weight going from the center, directly downwards. Weight directly downwards. We've got the contact reaction force on both wheels. Now he's driving along, so I'm not really sure. This one here, this one we're going to call driving force. Hasn't really got a name, that one, so we're going to call that driving force. But we do know that there's going to be friction at the tyres here, where the tyre meets the road. That's F for friction. And there's also going to be some air resistance. Air resistance. There's quite a lot on that one. We've got driving force forwards, friction and air resistance backwards. And then we've got weight downwards and reaction force going upwards. Next, we're going to have a look at the boat. The boat has got weight going downwards from the center of the object. And then we've got upthrust. Upthrust. Because the boat is floating. I'm assuming it's not moving. It looks like it's tied up. Okay, so the fish. Oh, there's a few here. The fish, I'm going to draw like this. I reckon there's some weight from the center of the fish downwards. Now there's something pulling it up. There's a fishing line. So here we've got a force tension pulling it up. Tension is pulling it up. Weight's pulling it down. Those forces are balanced, so the object is in equilibrium. Last one, the plane. The plane has got weight going towards the centre of the Earth. Now this doesn't have a contact reaction force. There's not in contact. If it was on the ground, it would have. But there's no shelf or table or ground, so there's no contact reaction force upwards. So the air actually pushes on the wings caused by the engine. This one here, we call it lift. I'm going to call that one lift. I'm going to call this one the force from the engine. Force from the engine going forwards. And going backwards, we're going to have, this is our drag, or our air resistance. Air resistance always goes in the opposite direction to which it's travelling. We've got push from the engine going forward, lift going up, and weight going down. This is a force that you've probably met in chemistry before, and physics, actually. We're talking about the force between a proton and an electron. So in our atom, we've got protons in the nucleus, and around the outside, we've got our electrons. We've got our protons and our electrons. Now, we've got a positive proton and negative electron. There is a force between them. So here, we've got a force between these two objects. And we call this one the electrostatic force. If you've had a look inside the nucleus, you might see there's also more than one proton. These are also exerting a force on each other. So they're kind of pushing each other away. And this is still the electrostatic force. So whenever we've got positive and a positive, or a negative and a negative, or a positive and a negative, these will make a force. We say it exerts a force on the other. And this is called the electrostatic force. Turns out this one here will repel, and these two here repel, and this one will attract. This one will attract. And this one will repel, as it says on the right. So we've got attract and repel, and the name of the force is electrostatic. Now this is a very different force. Lots of people think because there's a whole attract and repel, that magnetic force is very similar to the electrostatic force. It kind of is because it does that, but they're completely different forces. If you hold a magnet up next to an electron, it doesn't get attracted. It's not a magnetic thing. They're completely different. Electrostatic is positive, negative, and magnetic is north, south. Now they do similar things. So for example, if you have opposites, they will attract, and similar ones will repel. They'll still do that. But all we're looking at the moment is just the name. So if you hold up a magnet near another magnet or a magnetic object, there will be a force there, and it's called the magnetic force. Completely different to the electrostatic force. Okay, pause the video. Have a go at drawing these pictures and adding the force labels to it. You might start with the top left. You could say that there's a force here and a force here. Those protons are pushing each other away. And you could say that the proton and the electron are attracting each other. And this is called the electrostatic force. Electrostatic. Now you might say, hang on a minute, why doesn't the electron just zoom in, just smash into the nucleus? It's kind of because it's going around in a circle, a bit like the moon. The moon's attracted by gravity to the Earth, but because it's going round in a circle, it manages to stay in its orbit. So it's very similar to that, it orbits around in a circle. The next one on the top right, this is our magnetic force. They will be pushing each other away because they are both north, and this is the magnetic force. Bottom left, we have got a balloon. Now we could have the weight going downwards. I guess the up thrust is going upwards. Up thrust because it's floating. You might even say that if that's tied up, you could even say that there's some tension in the rope. So there's tension pulling that string. There's weight of the balloon going down. Up thrust going up. I'm assuming it's not moving, so we could say that they're balanced. Okay, the lion. The lion has weight going downwards. Weight. We have got reaction force going upwards. I'm actually going to draw it here. I should technically draw all four at his feet. I'm going to draw it like this, reaction force. I suppose I should have started it where the floor touches his feet. We have got, it looks like he's running. So we're going to have maybe some air resistance going backwards. We might have some friction going backwards from his feet. And he doesn't really have a driving force. Oh, this is a difficult one. The forward force, what's pushing him forwards? I'm going to call that force from his legs. Force from his legs going forwards. That's making it go forwards. We've got air resistance and friction going backwards. We got a reaction force, the contact reaction force going up, and the weight going down. Last one on the crane. Now, on the actual crane itself, you could have weight going down and the reaction force going up. You could also, if you wanted to, see over here, we've got maybe the weight of this arm, just this arm bit, this bit here. We could say that there's a force there, maybe there, causing that arm to fall down. There is a weight of maybe this hook on the end. That could have a weight as well. So it gets a bit tricky when you look at objects like this. We'll learn how to mix all these together later. All for now, all we're doing is labeling forces and drawing the arrows. So we've got some tension up here. So here we've got the weight pulling down and the tension going up. We've also got some tension here, and that's holding up this big boom here. And then we've got the weight and the reaction. I don't think it's moving, so I'm not going to add air resistance. I'm not going to add friction. I just think it's staying still right now. Okay, now you've named all of the forces. What I want you to do is have a think back at all of these forces and put them into two categories. The two categories we're doing is contact and non-contact. So have a think back at the diagrams, think back at the names. If they are contact, they will be touching. And if they are non-contact, they won't be touching. Try and put them into two categories now. And check your answers. If you got it right, give it a tick. If you got it wrong, correct your answer. You might notice I've put a few words up there that are the same. I put up there gravitational force and weight. They're the same thing. The force caused by gravity or gravitational force. I've also put up air resistance and drag. Same thing, technical words, you can use either. So contact is quite self-explanatory. If there's contact there, friction, tension, there has to be touching. Drag, air resistance, contact reaction force, up thrust. And the ones that don't need touching are the non-contact forces. These are electrostatic. The proton and the electron attract each other whether they're touching or not. Weight attracts. The earth is attracting my pen and it pulls it down. It doesn't have to touch, but there is a force there. And the magnetic force is, if you have two magnets, you probably felt the force. If you hold two magnets close to each other, there will be a force there, but they don't need to be in contact for there to be a force. Very good. Last thing, if you want to, you can have a look at some real life examples, try and draw them. If you want to have a go and get stuck, we can talk about them next time. We can talk about it in lesson. A couple of things to remember. The names are really important. The length of the arrows are important, and where you start the arrows from, also important.